Hello and welcome to today's video. Today we're going to be looking at principal stresses. This is the second of two videos looking at complex stress theory. In the first video we talked about a complex 2D stress system and how we could calculate what stresses were set up internally within a component at some plane. If we know the angle of that plane, theta, we can work out any direct stresses on that plane, any shear stresses on that plane. We looked at that for an element subjected to direct stress only. We looked at that for an element subjected to shear stress only, and then we combined those for a generalized 2D stress system. So we came up with a formula for being able to calculate what those normal stresses and shear stresses were internally within that component at some plane theta. What today's class is going to do is take that the result of that derivation and say, actually, as engineers, most of the time, it's not some stress at some random plane at some angle theta that we're interested in. What we're interested in is the part going to fail? Do we need to redesign the part to reduce the stress on it, or do we need to reduce the loading on it to reduce the stress on it? Is the part going to fail? So actually, it's not any stress at some random angle. It's the maximum stress. What is the maximum stress? So what we're going to do today, we're going to take the formula derived at the end of the last video, and we're actually going to differentiate that because that tells me the gradient of that function, the gradient of that line. We're just going to differentiate it and we're going to equate it to 0 because that is going to tell us the maximum or the minimum. The principal stresses are the maximum stress or the minimum stress, and they occur on principal planes. So what we're going to do today, we're going to take the complex stress equation derived at the end of the last video. We're going to differentiate it. We're going to equate it to 0. That's going to tell us our principal stresses. And then what we're also going to do is to work out where those occur, what the principal planes are, how we can calculate where the principal planes are, and any direct stresses and any shear stresses that result from that. So this is what we looked at last time. Here's an element subjected to normal stress only. We looked at that and said, okay, internally, if we cut that element through this plane AB at some angle theta, we can work out what the direct stresses are and the shear stresses are internally within that component. And we came up with those formulas. There's our direct stress, there's our shear stress, and we showed that our maximum shear stress is given by this. This occurs at 45 degrees, i.e. when this here is 1, and we've got a half sigma x minus sigma y. We then looked at an element subjected to to shear stress only, and again internally we cut this element at plane AB. We've got direct stresses and shear stresses, and we worked out that our direct stresses were given by this and our shear stresses were given by this. Okay, we then combined those to look at our generalized 2D stress system to show these equations here. Equation number 6 is our generalized for our generalized system, what our direct stresses would be. This equation here, this is the one we're going to be using today, actually, starting with today. And we also showed our shear stress is given by this. I then did some examples. I went through example 1 with you, I think, and then asked you to do examples 2 and 3 on your own. So hopefully you've done those. If you've not watched that previous video, if you've not tried those examples, please do that before attempting this video, this tutorial. Okay, so what we're going to do today is look at our principal stresses and our principal and where these occur, our principal planes. So the principal stress, the maximum and the minimum normal stress, the principal plane, the plane on which the principal stresses act upon. Okay, so this is the equation that we came up with last time. So equation number 6 here, this equation up here, sigma theta is a half sigma x plus sigma y plus a half sigma x minus sigma y cos 2 theta plus tau xy sine 2 theta. So you can see that's that equation there. That's where we're going to start today. So this is the equation that we derived last time. This tells us sigma theta, the direct stress at any plane at some angle theta, is given by this. And here it is in terms of sigma x, the stress in the x direction, sigma y, the stress in the y direction, and then we've got some trig here which basically multiplies this depending on what that angle theta is. And then we've got this term here, which deals with the shear stress. And again, we multiply that by some factor depending on what that angle is. Okay, so we've got some function, sigma theta, which tells us what the stress is, and it changes depending on what theta is. So if we were to draw that, all that we'd have is some function. If we let's how do I do that? Okay, so we've got some function which tells me sigma theta, and it changes as theta changes. And let's say our function might look something like that. Okay, but what we're interested in is not sigma theta, what is the stress at any plane. Generally, what we're interested in is this value here. What is the maximum value? This value here, look. What is that value there? What is the maximum stress? And do we need to be concerned? Is that likely to exceed the yield stress of the material? So that's what we're going to do in today's class. We're going to work out what that value is there, and that's called sigma 1. And where does that occur? Let's call that theta 1. So sigma 1 occurs at theta 1. What is the maximum stress? Is it likely to exceed the yield stress? And the way that we're going to do that, we're going to take that function and we're going to differentiate it. Because when we differentiate a function, it tells me the gradient of that function. And the gradient of that function here is positive. Here it's negative. Okay, and at the top here, it's 0. Okay, so we're going to take that function, we're going to differentiate it, we're going to equate it to 0, and at that position there, that must be the maximum or the minimum if this function were to continue. Let's draw it, let's carry on drawing it. Let's say it's doing this, and later on it starts to increase again. My gradient is also 0 here, isn't it? Okay, and that would be, talking in 2 dimensions, we would call that sigma 2. Again, let's call that sigma 2, and that occurs at that point there, and that would be theta 2. Okay, so my maximum principal stress occurs when the angle is theta, when the gradient is 0. It also occurs, the minimum principal stress also occurs when the gradient is 0. So when we take this function and we differentiate it and we equate it to 0, what we should end up with is a quadratic equation, i.e. an equation with 2 solutions. One is going to be the maximum and one is going to be the minimum. And that's exactly what we'll find today. So there's my equation that we're going to start with. There's my function which we're going to need to differentiate. We're going to take that function, we're going to differentiate it with respect to theta, and we're going to equate that to 0. So we're going to take all those terms there. That one is not a function of 0, so that term's just going to disappear. You can see that's happened there. There we've got half sigma x minus sigma y, that's just a number, times by cos 2 theta. So we're going to need to differentiate cos 2 theta with respect to theta. And then we've got a number there, tor xy times by sine 2 theta. So again, we're going to need to differentiate sine 2 theta with respect to theta. So let's recall some of our differentiation that we've done previously, and hopefully you're familiar with that. If y equals cos 2 theta, then dy by d theta would be minus 2 sine 2 theta. So cos becomes minus sine, and because we've got that 2 there, that 2 goes in front. So we've got minus 2 sine 2 theta. And what if y is sine 2 theta, sine becomes cos sine. So we've got cos 2 theta, and again, because we've got 2 theta, we take this 2 and we just put that in front here. So we end up with 2 cos 2 theta. Okay, so if we were to take this equation here and differentiate it with respect to theta, okay, we would end up with this. So this first term, you can see that's disappeared. And so now instead of having 1, 2, 3 terms, we've just got 2 terms. So this middle term, half sigma x minus sigma y cos 2 theta, that's going to become this, look. So cos 2 theta, you know, cos 2 theta becomes minus 2 sine 2 theta. So you've got minus 2. So 2 times by half would be 1. So that's where that half, that's why that half has disappeared. So you've got minus sigma x minus sigma y, and cos 2 theta, look, has become sine 2 theta. So this term here, differentiated it with respect to theta, has become this term here. And then the final term, the third term, this term here, we're going to differentiate that with respect to theta. And we can see that is here. So the 2 goes in front. So we've got 2 tor xy, sine 2 theta becomes cos 2 theta. So you've got plus 2 tor xy cos 2 theta. So all we've done there is we've taken the equation which we derived last week or last time, and we've differentiated it with respect to theta. So that's going to tell me the gradient of that function. Yeah, that's going to tell me the gradient, okay, anywhere. But we know for our maximum or our minimum that that gradient is 0. So that's where that 0 comes from. You can see there, suddenly, instead of writing d sigma theta by d theta, I've written 0 because it must be a 0 at a maximum or a minimum. And then you can see I've just copied it down. There's that term there, followed by that term there. Okay, and then we're just going to move that over to this side. So we've got it on there. So it was negative, it becomes positive. So there's that term there. And that blue term is still on this side, look, 2 tor xy cos 2 theta. If we then divide through by cos 2 theta, so we've divided through by cos 2 theta on this side, and we've divided through minus sigma x and minus sigma y on that side, we end up with this equation here. And then hopefully we can remember if we've got sine 2 theta over cos 2 theta, well, that's equal to tan 2 theta. Okay, so this equation here tells me the gradient of that function anywhere. As soon as we put that 0 in there, that's only true at the maximum or the minimum, okay, when the gradient is 0. So this here is only valid at the maximum or the minimum. Okay, tan 2 theta equals 2 tor xy sigma x over sigma x minus sigma y. Okay, so we've got that. We've shown for our maximum or our minimum direct stress, we've got this. Okay, now we know for the stress anywhere, so this is equation 6 from before, from the last video, anywhere sigma theta, so this tells me the stress at any angle, we've got that. What we're going to do now is we're going to say, well, we don't want to know the stress anywhere, we want to know what is the maximum stress or the minimum stress, what are the principal stresses. So in order to work out the principal stresses, let's take the stress anywhere and let's put in this relationship which we've just worked out, because that's only valid at those principal stresses. Okay, so we're going to put tan 2 theta equals that lot into this equation here. Okay, however, looking at that equation, we don't have tan 2 theta, we've got cos 2 theta. and we've got sine 2 theta. Okay, so what we're going to do now is we're going to work out what cos 2 theta. If this is true, what is cos 2 theta? And if this is true, what is sine 2 theta? Because then we can plug those values into that equation and we can work out what those principal stresses are, because those are only going to be true at our principal stresses. And we know that because we took that function and we differentiated it, we equated it to 0, and we came up with that lot. Okay, so remember, tan theta, the definition of tan theta, opposite over adjacent. So this here, I've drawn this. Okay, so imagine we've got our triangle. Instead of theta, we've got 2 theta. So I've written 2 theta here. Look, tan theta equals opposite over adjacent. Okay, so this must be the opposite side. This must be the adjacent side. Okay, so looking at my triangle, we've got 2 theta there. The opposite side is 2 tau xy. Okay, so there we can see that. Let's draw that in purple. That is the opposite side. Okay, opposite. And then the adjacent side, let's draw that pink. The adjacent side is going to be there, look. Sigma x minus sigma y, sigma x minus sigma y. There's my angle. Adjacent to that, we've got this length here. Okay, and that is the adjacent side. Okay, so this here is just, I've just drawn this equation essentially. Okay, and then in order to work out the hypotenuse, I've used a little bit of Pythagoras. So I'm going to take this side and square it. I'm going to take this side and square it. I'm going to add those two together and work out and then square root it. And that's going to tell me the hypotenuse. So you can see there, that's what I've done there. The hypotenuse is this side squared plus this side squared. Square root of all of that lot gives you that equation there. Okay, so we've now got a triangle which is only going to be true at our principal stresses. We know it's only going to be true at our principal stresses because we created that triangle from this equation here. Okay, but now we've drawn that triangle from this equation here, we can work out what cos 2 theta and sine 2 theta is. Okay, we know silly old Morris bought a herring trawling off Alaska, okay, or Sokotoa, or however you want to remember it. Okay, so cos 2 theta is going to be adjacent over hypotenuse. Looking at my triangle, that's the adjacent side, remember? So sigma x minus sigma y divided by hypotenuse. Hypotenuse is this big square root sign here. So there it is. There's that big square root sign. So that's cos 2 theta. And sine 2 theta equals opposite over hypotenuse. Opposite equals 2 tau xy, 2 tau xy over hypotenuse, which again is this big square root sign here. Okay, so we worked out this for our principal stresses. We've now drawn that, and then from that drawing, we can work out what cos 2 theta and sine 2 theta is. So what we can do now is we can go back to that equation, this equation here, and we can say, okay, well, that's valid anywhere. That will tell me the stress at any angle. But now for our principal planes, instead of writing cos 2 theta, I'm going to write this. So instead of writing cos 2 theta, I'm going to write this equation here. Okay, because that's true at our principal planes. And instead of writing sine 2 theta, I'm going to write that. Because again, that's true at our principal planes. Okay, so sigma theta equals that lot. So I've rewritten that equation, but instead of calling it sigma theta, I'm now going to call it sigma 1, 2. Sigma 1, 2 are our principal stresses. Sigma 1 being our maximum, sigma 2 being our minimum. Okay, So we'd expect two solutions actually, our maximum or our minimum. And then we've got a half sigma x minus sigma y, a half sigma x minus sigma y. So let's just zoom out a little bit so you can see that better. So that is there, look. And then we've got this red term here, a half sigma x minus sigma y cos 2 theta, a half sigma x minus sigma y cos 2 theta, remember, is this. Okay, so that there is there, look. That's cos 2 theta. That's that. Okay, and then we've just multiplied it by a half sigma x minus sigma y, a half sigma x minus sigma y. So that term there, hopefully you can see that's in its entirety is this term here. Okay, so that's that red term there. A half sigma x minus sigma y, a half sigma x minus sigma y times by cos 2 theta, which is this lot, times by cos 2 theta, which is that lot. And then in the same way with our final term, tor xy sine 2 theta, tor xy times by sine 2 theta is this now, remember? That's there, look. So that's sine 2 theta, sine 2 theta. And we've just multiplied it by tor xy, multiplied it by tor xy. So that term there is that last term. That term there is that term there. Okay, so before this was valid anywhere, sigma theta, some random plane theta, we worked out what our stress was in terms of sigma x, sigma y, and theta. Now, because we've plugged in these values for cos 2 theta and sine 2 theta, now that's only valid at our principal planes. Okay, and we've got this equation here. This quite horrible looking equation here, this big long equation here. But notice we can factorize that now. We've got sigma x minus sigma y squared plus 4 tor xy squared, the hypotenuse from that triangle. It's underneath this fraction. It's underneath this fraction here, look. Okay, so there we've got a half sigma x minus sigma y, half sigma x, half sigma x minus sigma y times by sigma x minus sigma y. So that is obviously sigma x minus sigma y squared times by half. Okay, notice I put that half outside that bracket and I'll explain why in a minute. Okay, but essentially if we were to multiply that by that, we'd end up with this lot. Okay, and it's over the hypotenuse. And then we've got 2 tor xy squared on the top here. So if we write 4 tor xy squared and multiply it by half, we're going to end up with 2 tor xy squared. Okay, and then again the hypotenuse underneath. Now the reason I did that, the reason I put that half outside of those brackets, is when you look at that now, hopefully you can see that the top term is simply the square of the bottom term. So we've got sigma x minus sigma y squared plus 4 tor xy squared. On the bottom we've square rooted it, so the top is just the square of the bottom. Okay, so if we're faced with that scenario, the answer is plus or minus the bottom. Okay, now that's maybe not immediately obvious, so let's put some numbers on it. Okay, so here we've got a number 25, and on the bottom we've got the square root of that 5, and the answer is 5. Okay, but if we took that number, the square root of that could also be minus 5. Okay, and the answer would be minus 5. So when you've got a number and the square root underneath, the answer is plus or minus that square root. Okay, so if we take the bottom term, oh sorry, plus or minus the bottom term. If we take that bottom term and we put plus or minus times by the hypotenuse there, the bottom term. Okay, so half sigma 1, 2, so our principal planes, our principal stresses are given by a half times by sigma x plus sigma y plus a half times by plus or minus the bottom term. And there I factorized it. You can see the half has moved outside the bracket because this is multiplied by a half and this is multiplied by a half. So that term there tells me the principal stresses. And that is that equation there. Okay, so before we worked out our stress at any plane, it's a function of theta. Now we've got our principal stresses. It's no longer a function of theta. We've removed that. It's just a function of sigma x and sigma y and tau xy. So if we've got an element subjected to 2D stress and we know what the maximum, we know what the stress is in the x direction, what the stress is in the y direction, and what any shear stress is on that element, I can tell you what the principal stresses are. The maximum stress, sigma 1, is when I take that term and I add that term. The minimum stress, sigma 2, minimum principal stress, is when I take that term and I subtract that term. Okay, so you can see there's two solutions. We would expect two solutions, one for sigma x, or one for sigma 1 and one for sigma 2. So we've now calculated what the principal direct stresses are on our principal planes, given this. Okay. What we might also need to find out, if we've worked out what our direct stresses are on those principal planes, what are our shear stresses on those principal planes? Now, we know for our generalized 2D stress system, which is this one here, our shear stress is given by this. So let's start with that equation, and then we've got sine 2 theta in there, and we've got cos 2 theta in there. So we're just going to plug in those values for sine 2 theta and cos 2 theta, which we calculated on our principal planes, and that will tell us what our shear stress is on our principal plane. Okay, so let's do that. There's that equation, and then we're going to plug in. Try and zoom out a little bit. Cos 2 theta, it's a red term. You can see that red term. Cos 2 theta is, sorry, it's sine 2 theta first. So sine 2 theta, let's do that yellow term first. Sine 2 theta, if I take that, you can see that that is, there, look. That is sine 2 theta, 2 tau xy, square root of, and then the hypotenuse. Okay, so we've got a half sigma x minus sigma y, a half sigma x minus sigma y times by sine 2 theta times by sine 2 theta. Okay, and then my cos 2 theta term, I do exactly the same. My cos 2 theta term is there, look. So it's sigma x minus sigma y on the top, sigma x minus sigma y on the top, and then the hypotenuse on the bottom. Okay, so that there is clearly cos 2 theta on my principal planes. Okay, so if we now look at that, so we've got this equation here, which is valid anywhere. It's my shear stress anywhere. This equation here now tells me my shear stress on my principal planes, because we've replaced sine 2 theta and cos 2 theta with these two terms here. If we now inspect that, if we now look at that, on the top we've got a half sigma x minus sigma y times by 2 tau xy. Clearly the half and the 2 are going to cancel out. That's going to be equal to 1. So we've got this bracket, sigma x minus sigma y times by tau xy. On this side, we've got tau xy times by the bracket. It's going to be the same. Okay, two numbers. Here we've multiplied them. Here we've multiplied them just the other way around. Okay, and then on the bottom, they've both got the same term, this hypotenuse. So we've got some number, subtract the same number. Okay, so the answer is clearly going to be 0. So what does that tell us? On our principal planes, we've worked out what our direct stress is. It's given by this, and our shear stress on our principal plane is equal to 0. So on our principal planes, they are acting exactly the same as if our element is subjected to direct stress only, because there is no shear stress, it's subjected to direct stress only. So let's have a look at our element subjected to direct stress only, and we can work out what the maximum shear stress is. Okay, and that occurs at 45 degrees relative to that plane. Okay, so our element subjected to direct stress only, there's my maximum shear stress, a half times by sigma x minus sigma y. Sigma x is going to be the stress along that plane in the x direction. Sigma y is at 90 degrees to that. Okay, so when we're talking about our principal stresses, sigma x, the stress along that plane, is going to be the maximum stress, and sigma y is going to be the stress at 90 degrees to that, i.e. the minimum principal stress. Okay, so there we've drawn that. Okay, for maximum shear stress equals a half sigma 1 minus sigma 2, and that occurs at 45 degrees to that plane. Okay, so let's now plug in our values for sigma 1 and sigma 2. We calculated those up here, look, sigma 1 and sigma 2. Sigma 1 was when we took that term and we added that term. Sigma 2 was when we took that term and we subtracted that term. If we now put those in there, and looking at that equation, there should actually be some more brackets around there. There should be additional bracket around there, look. Okay, so we've got a half plus that term minus, and in brackets now, a half minus that term. If we now do that, if we look at that here, this first term clearly cancels with this term here. Okay, so we've got a half sigma x minus sigma, half sigma x plus sigma y, subtract a half sigma x plus sigma y. So clearly they're going to cancel out. This second term here now, we've got a half of this square root minus a half of this square root. Okay, so that's going to be a half of that square root plus that square root. So the answer is just that square root. Okay, and then we've got this half outside the brackets here, so that's where that half comes from there. Okay, so looking at that lot, we can simplify that. So that's the maximum shear stress, and that occurs at 45 degrees to the principal plane. And there it is in terms of sigma x and sigma y and tau xy. So to summarize, what have we looked at over the last couple of videos? We've seen this. We've got our stress on any plane. It's given by that. It's also given by this. The direct stress is given by that. The shear stress is given by that. The maximum shear stress occurs at 45 degrees, and it's given by that. So there was our element subjected to normal stress only. Our element subjected to shear stress only, we derive these two equations. To get our generalized 2D stress system, we just combine them. Okay, so for our element subjected to normal stress only, our direct stress was given by that. And for our generalized 2D stress system, we can see that is there. Okay. For our element subjected to shear stress only, the direct stress internally is given by this term here. There we can see it. Okay, so for our generalized 2D stress system, we've just combined our element subjected to direct stress only and our element subjected to shear stress only. What is the direct stress internally? It's given by that. Okay, same for the shear stress. For the element subjected to direct stress only, the shear stress internally is going to be given by that. And that is there, look, a half sigma x minus sigma y, a half sigma x minus sigma y times by sine 2 theta times by sine 2 theta. Now elements subjected to shear stress only, internally, the shear stress is given by that. And there it is. Okay, so for our generalized 2D stress system, we've just taken our element subjected to direct stress only, and our elements subjected to shear stress only, and just combine those two equations to get a generalized equation. What we've done in today's class now, we've taken that equation there, equation 6, I think it was. So our direct stress on any plane, we've differentiated it with respect to theta. We've equated it to the 0. We've worked out what cos 2 theta is and sine 2 theta is, plugged that back into that equation, and we've ended up with this. So this tells me my principal stresses for my generalized element. Okay, notice there's not theta in that equation. We've then also worked out what the maximum shear stress is. It's given by that. Okay, so we've taken that equation and we've plugged in sine 2 theta and we've plugged in cos 2 theta, and we've ended up with that. The other observation that we've also shown is that on the principal planes, the shear stress is 0. So the last thing we're going to do today is to work out where those principal planes occur. So just like we were doing in the last video, let's take our element subjected to a 2D stress system. We've got some direct stress, which we'll call sigma x. We've got some direct stress in the y direction, which we'll call sigma y. We've also got some shear stress. We've got shear stress on this plane AC, tor xy. And we've got some shear stress on this plane here, CB, which is also tor xy. Okay, if we want to know where those principal planes are, what we're interested in is finding out this angle theta. And we've drawn my principal plane there, AB, and my principal plane has got a principal stress on it, which we'll call sigma p, and we've got a shear stress on it, which we've just shown that our shear stress is going to be equal to 0. Okay, so there is my free body diagram of my element in my generalized 2D stress system. I happen to have cut it through plane AB, which is a principal plane, therefore it's got principal direct stress or principal stresses on it, direct stresses shown by this, and shear stresses are equal to 0, and it's at some angle theta, and we want to be able to work out what that angle theta is. So we know this is in equilibrium, so therefore all of the horizontal forces are equal, i.e. that they add up to 0. All of the vertical forces are equal and they add up to 0. The thing is set in equilibrium. We could also take moments. We know the clockwise moments are equal to the anti-clockwise moments. Again, it's set in equilibrium. So we can do any of those things to work out what theta is. What I've then shown here in these notes is, okay, one example, I can work out what it is if I resolve it horizontally. So if I'm resolving this horizontally, sigma y has no horizontal component, so therefore that's not going to appear in my final equation. So I only need to consider these terms here: sigma x, tor xy, and sigma p. Okay, so resolving horizontally, the forces to the left are going to be sigma x, that's the stress. So to get the force, we've multiplied by the area. Remember, this was unit thickness in the same way that we looked at elements which were unit thickness in the last video. The area of this triangle or the surface on this triangle would be A times by C times by 1. A times by C times by 1 times by the stress. So that's going to give me the force caused by sigma x acting in that direction. So that term there is going to be the force caused by that stress, plus tor xy times by BC times by 1. That is the force caused by this shear stress. Now, the shear stress on plane AC, clearly that has no horizontal component, so I only need to consider the shear stress on plane BC. So if I take the shear stress and multiply it by the area is going to be B times by C times by 1. B times by C times by 1. That's going to be the force to the left caused by the shear stress on plane BC. That is going to be equal to the horizontal component caused by the principal stress on that plane. So I'm going to take sigma p, that's my principal stress, multiply it by the area, A times by B times by 1, to give me my force caused by that principal stress, and then I'm going to take the horizontal component, so I'm going to move it down through this angle to work out what this component here is. I'm going to move that through the angle there, which is going to be theta clearly. Okay, so we've got CP, sigma P, AB times by 1, that's the force, times by cos 2 theta, that's the horizontal component of that force. Okay, if I now simplify that, I've got AC sigma x plus BC tau xy plus AB sigma P times by cos theta. If I divide through by AB, just like we were doing in the last video, I've got AC over AB sigma x, BC over AB tau xy equals sigma P cos theta. We know from our last video, this ratio, AC over AB, was equal to cos theta, and BC over AB was equal to sine theta. So therefore, I'll just plug those in there. I've then divided through by cos theta. So we've got sigma x divided through by cos theta. Here we've got tau xy sine theta divided through by cos theta. And here I've divided through by cos theta as well. So I've just got my principal stress. Sine theta over cos theta is clearly tan theta. So sigma x plus tau xy tan theta equals my principal stress. And therefore I can rearrange that to get that equation there. And what that equation there enables me to do is, if I've worked out what my principal stress is, and I know what my stress in the x direction is, and my shear stress on the xy plane is, I can work out what theta is, where my principal plane is. Okay, now here I've resolved horizontally, so I've only got sigma x in this equation. If I'd resolved that vertically, I would have sigma y in that equation, okay, instead of sigma x. Okay, but what that enables us to do is to work out where those principal planes are. Okay, so let's have a think about what we've done over the last couple of videos. We considered an element subjected to normal stress only, and we worked out what the direct stress was and the shear stress was internally at some angle theta. We then said, okay, let's take an element subjected to shear stress only, and let's work out what the internal direct stress and shear stress was. And then we combined those and we came up with those two equations there. What we've done today is we've taken those equations and we have said, okay, well, let's work out what cos 2 theta and sine 2 theta is on our principal planes, plug those back in, and we ended up with our complex stress equations. Okay, so there's our principal stresses. And we worked out what our shear stresses were. And then the last thing that we've done today is we've worked out where those principal stresses occur. Okay, so at the end of the last video, I went through question number 1. I wanted you to have a look at questions number 2 and 3. And you'll see in this handout now, there are 4 principal stress questions. And I'm going to do the same thing. I'll have a look at question 1 with you, and then I want you to have a go at question 2, 3, and 4. And because we've gone through and we've derived those equations today, you've seen how we've done that. You should be able to successfully use those. I don't expect you to remember them. I don't expect you to remember those big long equations, but you should successfully be able to use those. So let's have a look at question number 1. So under certain loading conditions, the stresses in the wall of a cylinder are as follows. We've got 80 megapascals in tension, 30 megapascals tensile at right angles to position A, to the stress described in A, and then shear stresses of 60 megapascals on the planes on which the stresses A and B act. The shear couple acting on the planes carrying the 30 megapascal stress is clockwise in effect. So that enables us to understand the relative direction of the shear stress relative to the orientation that our element is sitting. Calculate the principal stresses and the planes on which they act. What would be the effect of these results if, owing to a change of loading, A becomes compressive whilst B and C remain unchanged? Okay, so let's have a look at that first part together, and then I'll let you have a look at that second part once, what would happen if we reverse the loading. Okay, so let's have a look at that. We have a look at your notes. Here we are, question number 1. Okay, so we've got 80 megapascals in tension in one direction, 80 megapascals in tension. Okay, so there's our 80 megapascal load. We've then got 30 megapascals tensile at right angles to that. So there's my 30 megapascal load at right angles to that. And then we've also got a shear stress, the shear stress of 60 megapascals on the planes on which the stresses A and B act. The shear couple acting on the planes carrying the 30 megapascal stress is clockwise in effect. So the plane which is carrying the 30 megapascal direct stress is carrying a shear stress which is trying to rotate the element in a clockwise direction. So the orient, or that description there, tells us the direction that shear stress is acting in. So let's draw our element like that. We can then take the equation which we've derived today, and we can work out what those principal stresses are. The maximum principal stress, sigma 1, is when we take that term and we add it to that term. The minimum principal stress is when we take that term and we subtract that term. So the way we've drawn it, sigma x is 80. I've noticed all my stresses are in megapascals here, so my answer is going to be in megapascals. Okay, so sigma x is 80, sigma x is 80, sigma y is 30, sigma y is 30. So we've got 80 plus 30, so we've got 110 in this first bracket here. And then this second bracket, this second term, which is this hypotenuse term, we've got sigma x minus sigma y. So that's 80 minus 30 squared, plus 4 times by 2xy squared, 4 times by 60 squared. And if we calculate all of that square root time there, we're going to get 130. So the maximum principal stress is going to be 110 plus 130, half of that, so that's 120. And then minimum principal stress is going to be 110 minus 130, and then half of that. So we end up with minus 10. All this minus sign means is it's compressive. Okay, we've assumed all along in all of this stuff that a positive stress is a tensile stress and a negative stress is a compressive stress. So we've got sigma 1 and sigma 2. Okay. The question goes on to ask, calculate the principal stresses and the planes on which they act. So in order to get the plane on which sigma 1 is a maximum, the plane on the maximum principal stress, we're going to put in principal stress 120. So we've got 120 minus 80. That was sigma x divided by 60, tan to the minus 1 of that. So my maximum stress occurs at 33.69 from the vertical. Remember, that's how we defined where theta was created. It was from the vertical plane. And in order to get the minimum principal stress, the position of the minimum principal stress, we're going to take the minimum principal stress, which we've just calculated, is 110. So we're going to put in 110 minus sigma x minus 80 divided by 60, tan to the minus 1 of that, which gives me minus 56.3 degrees. So what does all of that tell me? So let's draw our element. We've got I draw my element in red here. In this direction, we had what was sigma y as we drew it was 30 megapascals, wasn't it? So we've got 30 megapascals there. We've got 30 megapascals there. Sigma x in this direction. Sigma x in this direction. As we've drawn it, sigma x was 80 megapascals. So we've got 80 megapascals. we've then said, okay, well, if we were to draw our principal plane now, let's draw our principal plane down there. We are interested in what is that angle on that principal plane and what are the stresses on that principal plane. We've just calculated that when that angle there is, so we consider sigma 1 first. So when that's 33.69 degrees, 33.69 degrees, 33.69, and that's 33.69 degrees. The principal stress was 120 megapascals. So we'd have 120 megapascals there. Okay, now we know my shear stress is going to be 0 on that plane. Okay, the other stress, so that's the maximum principal stress. So I've now drawn the maximum principal plane and the maximum principal stress on that plane, and we've worked out that that is 33.7 degrees, 33.69 degrees when measured anti-clockwise from the vertical plane. Let's now look at the minimum principal plane. Okay, now the minimum principal plane was at minus 56.3 degrees. Minus 56.3 degrees. If I were to draw that, that would be, let's pull that in pink here. That would be in this position here. There would be my minimum principal plane. Okay. Now that is minus 56 degrees here. Minus 56.3. Minus 56.3. Okay. So I could measure minus 56.3 degrees here, or to get to the same position, that would obviously be in this direction. A positive angle would be 180 minus 56.3 degrees. So if I consider this angle here would clearly be 56.3 degrees. 56.3 degrees. So a positive angle would be 180 minus 56.3 degrees. So 180 minus 56.3 is going to be 180 minus 56.3 will be 123.7, and that's where that comes from, 123.7. So 56.3 degrees, that's when we're measuring clockwise from the vertical plane, and 123.7 is going to be when we're measuring anti-clockwise from the vertical plane to get to the same location. Notice those two planes are at 90 degrees to each other, and that's exactly what we'd expect. The principal planes are always at 90 degrees to each other. The maximum principal plane has a stress of 120 megapascals. The minimum principal plane, we've worked that out as minus 10 megapascals. So that plane is going to have a stress of compressive stress, that's why it's negative, of 10 megapascals. Okay, so the maximum principal plane is at this angle and has got a tensile load on it. The minimum principal plane is at that angle and has got 10 megapascals compressive stress on it. So what I want you to do now is, so that's where those come from. the rest of the question, depends on which that. What would be the effect on these results if owing to a change of loading A becomes compressive whilst B and C remain unchanged? I want you to have a go at those. Okay, so the solutions are there for you to try those. The work solutions, I'll upload those to Teams, have a go at those, and then also have a go at questions number 2, 3 and 4, which will show you how we can go about using those equations which we've gone through and derived today. Okay, have a go at those questions, and we can discuss those when we meet.